introduced by Senzi. So Dr. Senzi, as I mentioned earlier, he got his PhD at UCLA under the supervision of Terry Tao. And we actually had a very interesting conversation yesterday about the teaching of calculus. So I mentioned I'm teaching calculus this semester, and I used the book of Columbus John. And he mentioned, because he got his bachelor from Princeton, and he said they use directly the decoupling for the last year calculus. I think it's more tough. But anyway, so yeah, Dr. D has been working on a very important and active topic in the area of computer analysis about the decoupling inequalities. And he's done very good result in this area. So we are very pleased to have him to speak, introduce some of his work on the decoupling inequalities. So let's welcome Dr. Lee.
Yeah, thanks for the nice introduction. Yeah, so in the series of 5 lectures, I'll try to introduce sort of decoupling inequalities. Now, the abstract I wrote was a bit ambitious, I think, so we'll see how much we can actually cover. So what I try to aim to do is, the arguments that I give. So in decoupling, in the area of decoupling, there are a lot of times people use a lot of these back of the envelope calculations, a lot of these heuristics, but they're often not stated, or they're not stated in that it's made completely rigorous in the paper. So what I want to also try to do when I give my lectures is that I want to try to mention these back of the envelope calculations and sort of mention how one makes it rigorous, but I might not make it completely rigorous because that would sort of obscure all the back of the envelope calculations that we really do all the time. Okay. Now, in the papers, especially the ones that I cited, they're all made completely rigorous. If you want the complete, full, maybe too much details version, you can look at the papers. But here in these lectures, I want to try to aim to give these heuristics. And I'll actually write down the heuristics that we use and what those statements are. But before we get started, let's even try to answer the question, what is decoupling? So what is decoupling? Okay. So let's first talk in more general terms. So we're going to let omega be a region RD. And we're going to partition into a collection theta. Right? So stereotypically, it's some blob here, omega, and we cut it up into regions theta. And we're going to define on the Fourier side, so we're going to let f theta hat be defined to be f hat times the indicator function of 1 theta. Oftentimes, when I write indicator function, you might not want to think that it's a sharp cutoff. You could use smooth cutoffs if you want. We're not going to care so much about sharp versus a Schwartz function that's adapted to theta. Fine. It's just convenient to think about it if it's a sharp cutoff. But technically, it's better if it's a Schwartz function. Anyways, so we're going to let dp, now the decoupling constant, depends on the LP norm, it depends on the omega, and it depends on the particular partition, be the best constant such that the LP norm of f is broken up, and dp is the cost, is broken up into the thetas, and I measure this in little L2 for all f with Fourier transform supported in omega. Oftentimes, the shorthand for what people say, this sentence, for all f with Fourier transform supported in omega, people just say for all f Fourier supported in omega. Okay, so why is this called decoupling? Why is, and implicitly, we always want to assume that t is between, let's say, 1 and infinity, so that we're working with Lisa Banach space. Why is it called decoupling? Right? Where does the word come from? Well, it's called decoupling because let's say I want to study the LP norm of F. Then I have this estimate. And then what this estimate does is that, well, in order to study F at the cost of dp, all I have to do is study the LP norms of these F thetas. Maybe that's an easier piece, right? I initially wanted to study the LP norm over this whole region at the cost of dp, which we would love to imagine to be small or negligible. Then this inequality says that it suffices to study the LP norm of each of the individual pieces, which is much smaller. So maybe the problem has gotten easier. Okay. This is a very abstract setting. Okay. So, okay, what else do I want to say? This is called an L2 LP decoupling theorem because of little L2 here. These estimates were sort of first studied by Wolf in 2000, who first proved a LP-LP decoupling for the cone. So typical examples of omega are sort of, they come from various problems, like if you want a certain thin neighborhood of the paraboloid, that comes from wanting to study the Schrodinger equation, the moment curve. When omega is the moment curve, that comes from Vinogrado's mean value theorem. When omega is the cone, that comes from the wave equation. So there are certain problems that tell us which omega and which theta to study. Okay. Okay. Oh, I guess if I put it too high, the lights will block. Okay. 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 So at this general level, there are some easy observations, right? First of all, D2 is equal to 1, right? This is just Plancherel. I can always have L2, L2 decoupling, right? This is Plancherel. Okay. And we at least have the trivial bound that the decoupling constant at this generality is always bounded by the number of pieces to the 1/2. This is via the Cauchy-Schwarz inequality. Right? Basically because you know here, for all F with Fourier transform supported in omega, then I know that F hat is equal to F hat times indicator omega, which is sum theta F hat times the indicator function of theta, which is sum theta hat. Right, so I can always have a trivial estimate that the decoupling constant is at least finite. It's bounded by the number of pieces to the 1/2. Okay, and great. So at this generality, there's nothing much else we could say, at least right now. There is this sort of theory of everything where that given certain caveats, you can decouple literally anything, so that is probably beyond reach at the moment. So what we're the focus of the next, today's lecture and next week's lecture will be on decoupling for the parabola. So, so what kind of specific decouplings are we going to try to aim to prove? So we concentrate on decoupling, I'll often abbreviate DEC. For the parabola in R2. Okay, this estimate was, so I'm only giving you the omega. I haven't told you how I've partitioned it. We'll be more precise later. So we concentrate on decoupling for the parabola R2, which was first proved by Morgan and Demeter in 2014 as a subcase of their paraboloid decoupling theorem. Second, I'll probably mention how one proves decoupling for the moment curve in R3, which is the curve T maps to pt squared T cubed. And this was also first proved by Morgan, Demeter, Guth. in 2015, in December of 2015. And we'll also concentrate on decoupling for the paraboloid in R3. This is the surface ST maps to ST S squared plus T squared. And this was also first proven by Morgan Demeter Guth in 2014. The proofs that we'll cover are going to be a bit different. So for the parabola, we're going to cover the short proof that the sort of number efficient congruency inspired proof of parabola in R2 that I have, though I'll also mention similarities and differences between the 2014 proof. The moment curve in R3, we're going to cover the short proof of decoupling for the moment curve written by myself, Xiaoming Guo, Pelem Yang, and Pavel Zorn-Krenich. And then the paraboloid in R3, we're going to illustrate the original Morgan-Demeter paraboloid proof, if we get that far. Of course, probably what's going to happen is that we're going to concentrate on these two, and I'll mention the ideas of two. Yeah. Okay. Any questions?
So,
yeah.
Omega is in Fourier space here.
Yes. Yes. So f hat lives here. Right. So this
so
is
support of f hat is an omega.
Yes. Support of f hat is an omega. Support of f hat is an omega. Right, so or often I'll just say that f is for a supported in omega.
Okay.
Yeah. Okay, great. So this lecture we're going to concentrate on this, and probably also at least the first half of the next lecture, if not the whole of next lecture, since I want to do some details. So let's talk more specifics about the parabola in R2. It's the sort of the easiest decoupling beyond just Plancherel. Okay. Let's see. How do these boards work? Well, I guess I can write here. But if I'm too short to write. I guess I'll write here and then move it off. Yeah. I don't think. Yeah, okay. Okay, so let's talk about decoupling for the parabola. Okay, so I've only given you a surface. I haven't even given you an omega or a theta. So what's the particular omega? So let's draw a picture first. Yeah, let's draw the picture first. So any compact subset of the parabola will work. Well, okay. So I'm actually going to pick the piece of parabola that lives above 0, 1. And I'm going to pick a delta squared. So delta will be a small parameter. Small. Okay, and I'm going to pick a delta squared neighborhood of the parabola. So this is a delta squared neighborhood of the parabola. This is my omega. Okay, is there any colored chalk? Yes, there is. Okay, that's an omega. Okay, and what do I pick as my theta? Well, what I do is I partition 0, 1 into intervals of length delta. Each of those intervals lifts to a neighborhood a piece in this omega. Right, so here's a theta, here's a theta, here's a theta, here's a theta, here's a theta. Right. Does that make sense so far? Okay, so let's be more precise, or slightly, let's write down something. So omega is the delta squared neighborhood of the parabola above 0, 1. Or more precisely, it's just s squared plus t. S is in the unit interval. T is less than delta squared. Okay. And what are the thetas? Notationally, P delta will be defined to be the partition of 0, 1 into intervals of length delta. Okay, this is just notation. And of course, if I write p delta of I, that means I partition I into intervals of length delta. Okay. Partition I into ints of length delta. Okay. And then let me write the thetas, and then I'll move the board out. So temporarily, I'm going to cover up the definition. Theta I, so for each I in p delta, theta I will be the delta squared neighborhood of the piece of parabola, SS squared, that lives above I. Or more precisely, it's just S squared plus T. S is in I. T is less than delta squared. Okay. Let me move this up. Okay. So strictly speaking, I've sort of defined these neighborhoods so that they don't have any overlap. They're very precise, right? Now, in reality, decoupling is very forgiving. They allow little finite overlaps. That's okay too. Okay, but here I'm just trying to give the most simple, basic, complication-free version. Okay. Now, let me write down the decoupling constant. And then let's talk about, why this neighborhood and so on and so forth. Okay. Yeah. Okay. Okay, so we're going to so we have an omega, we have a partition, now we're going to define a decoupling constant. So for p bigger than 1 and less than or equal to infinity, let dp delta be the best constant such that the LP norm of f is controlled by dp delta sum theta, f theta, sum I in p delta, f theta I, in big LP little L2, for all f with Fourier support, for all, let's use the language already, for all f Fourier supported in omega. So dp delta is the best constant that I can put here for all f with Fourier transform supported in this delta squared neighborhood of the parabola above 0, 1. Okay, yes?
So all omega is also depends on delta.
Yes. So I fix the delta. Okay, so of course if you pick delta equals 1, right, or delta equals an actual number, like delta equals 1/2, then you pretty much know that the decoupling constant is going to be of size 1. Right? It's going to be some constant bounded above and below by 1. Well, we'll talk about upper and lower bounds. The idea is that we want to get an estimate that sort of looks at the dependence on delta. Right? If you say, I want to know what decoupling is at scale 1 million, right? Unless if you want explicit constants, you know that that decoupling constant is going to be of size 1, like a big O of 1, some constant. Yeah. Any other questions? Okay.
How does the, if you prove it for size 1 and then you rescale the inequality, how does that appear?
Like if you prove this?
If you prove it for constant 1,
Uh-huh.
and then you rescale the neighborhood,
Uh-huh.
does it tell you anything?
No, because then you're just left with, so let's say you're able to prove this thing for like half the interval. Right? Well, then you're basically done with it. If you knew how to decouple half an interval, then you just you apply a change of variables, stretch the little parabola a little bit, and then you'd be able to know how to decouple the whole 0, 1. Right?
I see. So what you're saying is because you want to get the whole interval, or the whole parabola all the way up, and that's why.
Yeah, so the idea is that, so we'll talk about the estimates, but we want an estimate of the form like, the decoupling constant, dp of delta, is controlled by like delta to the minus epsilon, or some power of delta, right? So if delta was of size 1, like a half or a quarter or something, that doesn't say much. It just says that dp of a quarter is controlled by a constant, which you could just see just from here, right? So if I told you, okay, if I was an interval length 1/2, if my thetas was just length interval 1/2 and interval 1/2, then just by the trivial bound, dp is controlled by 2 to the 1/2, right? So that's also a constant. So up to, like, constants, so we're going to ignore all constant multiples. Up to constants, we have already the sharp result. Right? Okay, so we've written down the decoupling constant. We've defined our omega, and we've defined our regions theta that we want to partition into. Okay, so now let's pause, and one may start wondering, why are we even talking about a delta squared neighborhood? Why not a delta neighborhood, or why not a delta cubed neighborhood, or a delta millionth neighborhood? Or why not just straight up just the parabola, right? And with delta squared is sort of the right scale, because let's draw a piece of delta. Let's draw a little piece of theta. So theta corresponds to interval I. This is of length delta. This is a delta squared neighborhood. Okay, delta squared. And so because I'm on a compact subset of the parabola, okay, this length is delta, so that means this sort of horizontal length is also delta, up to constants. Okay. So we pick a delta squared neighborhood because it's at this scale that sort of this piece of parabola, this neighborhood of the parabola, is like sort of locally flat, right? In the sense of this piece, this delta squared neighborhood is sort of contained inside, contains a parallelogram, and sort of is contained in a giant parallelogram, right? So in other words, even though, yeah, like it's a delta squared neighborhood, it's sort of curved, okay? It more or less acts like a parallelogram. It acts like a rectangle. And Fourier transform works really well with like rectangles and boxes and lines, linear things. Right? Okay, so that's why a delta squared neighborhood rather than, let's say, a delta cubed neighborhood. If you picked a delta cubed neighborhood, you couldn't fit a parallelogram inside it. Right? That you start seeing the curvature of the parabola. Yeah. Great. Okay, so now what's the Bourgain-Demeter decoupling theorem? Okay, so theorem, Bourgain and Demeter, 2014. For p bigger than 2, the decoupling constant is controlled by delta to the minus epsilon times 1 plus delta to the minus 1/2 minus 3 over p. And what is this notation? So I'm going to use this notation a lot. So if x and y are positive numbers or expressions, okay, I'm going to write x less tilde y if there exists a c such that x is less than c times y. Okay, so these are non-negative. Okay, this is just notation, so we're not going to keep track of multiplicative absolute constants. This is absolute constant. And if I write x, let's say tilde a y, then if this means that if there exists a constant depending on a, such that x is less than CA times 1. Okay? I'm not going to keep track of any of these constants ahead of it. So then this says that dp of delta is bounded by a constant depending on epsilon, delta to the minus epsilon times this guy. Okay?
So the constant is worse even for bigger to 2. I mean, for bigger to 2, we often decoupling comes by 1. But
Yeah, so yeah, so the interesting portion is really when it happens when these two are equal, when p equals 6. Right? Yeah, I mean, strictly speaking, like, this is, yeah, I mean, you could say p strictly bigger than 2, and then d2 is bounded by 1, right? But d2, no one is interested in, right? Yeah. So I'm going to write it this way. Yeah. In fact, at infinity, it's also worse, too, because at infinity, you get delta to the minus 1/2 minus epsilon, but really the Cauchy-Schwarz inequality gives a better estimate. So really, this is an estimate for for non-trivial p, right? So for p and not the endpoints. Okay, and so what we're going to do is for the rest of the talk today, or for the rest of the first hour, we'll see how far we get. I'm going to mention that we can ask, well, is this sharp? Is this the right bound to have? Okay. So currently there are 3 proofs of this. In the case of the parabola, there are 3 proofs of this estimate that are all somewhat different. There's the original 2014 Bourgain-Demeter proof as the special case of their paraboloid proof. There is my proof in 2018, where I gave a proof of this using ideas from the number theoretic efficient congruencing. So we're also going to talk about relations between this proof and sort of number theory and how those ideas help me give a new proof of this estimate. And then there is a third proof by Larry Guth, Dominique Maldog, and Hong Wang in 2020. So Bourgain-Demeter's proof dates to 2014. My number theory implied proof of this dates to 2018. And in 2020, Guth, Maldog, and Wang, they proved an estimate. They gave a third proof of decoupling for the parabola, where instead of a delta to the minus epsilon, they replaced this with some power of log. Okay, so their proof was extra efficient. The downside of their proof is that their proof doesn't generalize to paraboloids or moment curves, at least as of right now. Okay, so that's just some side remarks. So we're going to aim to prove this theorem. Okay, so let's first, before we prove this theorem, I'm going to try to mention, is this theorem sharp, right? If you prove an upper bound, yes.
So do we know whether this bound is sharp?
Yeah, so we do. So that'll be the topic of what I'm going to talk about next. This bound is sharp up to delta to the minus epsilons. In fact, what I'm going to do is I'm going to show you that dp of delta is actually at least bounded below by this term over here. This term over here. Okay, so up to delta to the minus epsilon, you have that dp of delta is at least this guy, and it's bounded above by delta to the minus epsilon times this guy. So it's sharp up to delta to the minus epsilon losses, which in the decoupling world we claim as victory, and that's sharp. And I do that because that's a good way to introduce the heuristics that are used in this field. Okay? So let's introduce some heuristics. Often, so there are often 2 ways to approach. There are 2 ways to exposit why this is the lower bound is sharp. You can either do it completely rigorously, or you can do it the way I'm going to do it, which is the back of the envelope calculations that sort of I think are useful to see and learn from. Okay, so so to see let's first discuss 3 heuristics. Okay? And you can, of course, make all this rigorous, but I'd rather not present the rigorous version. I'd rather present the heuristic version, just to illustrate how a lot of decoupling is done, at least on the first pass. And then when you write your paper, you write it rigorously. Okay, so let's talk about 3 heuristics. So heuristic 1. So we don't distinguish between squares and circles and circles. Okay, nor the interval, let's say, minus r to r and 0r. Our analysis will be blind to what's a square and what's a circle, or is it an interval length 2r or interval length r. These are all the same object. Okay. So when I write b0r, is this a ball of radius r? Well, that's the same as the square of size r centered at the origin. And it's also this r ball at the origin are all the same. Are all the same heuristically. Okay, and we also don't distinguish between r and 2r. Okay, they're all conveniently, if you want really explicit constants, like if you really want to write down, is dp of delta bigger than 10 to the million times this guy, then yeah, you do need to distinguish. But thankfully this conveniently, at least at a heuristic level, allows us to sort of not care about r and 2r, not care about a ball of radius r, the box of size 2r centered at the origin, and the box of size r with the left endpoint at the origin. I'll often use these interchangeably. Okay, I hope this is acceptable. Okay, let's slowly ramp up the heuristics. So heuristic 2 is that the Fourier transform of the unit ball, what is this? Well, we know that this is the sinc function, but heuristically this is basically the unit ball. So let me say why, because yeah, the sinc function is not the indicator function of the unit ball, but let's say why. So whenever I write down an indicator function, you think that really it's a Schwartz function that's adapted to, so it's equal to 1 on the ball of radius 1 and then rapidly decays outside. So let me verbally say it first. So if I take a Schwartz function that is equal to 1 on the unit ball and rapidly decays outside of the unit ball, like it's 0 outside of 1.0001, what's the Fourier transform? Well, the Fourier transform is basically 1 out in the unit ball, and it's a Schwartz function, so it decays rapidly outside, a ball of radius 2 or something. That's basically the indicator function of the ball, because we don't distinguish 1s and 2s. Right? So that's roughly why I'm going to say this heuristic. So just to put more details to that, there are, okay. So y, we're going to let eta b01 equal 1 on b01 and decays rapidly outside b01. Okay, and it's a Schwartz function. Okay, well then what's the Fourier transform? Well, we just do calculus. Eta b01 hat of c. Well, this is just eta b01 of x, e of minus x dot c dx. And what is this notation? This is e of z is the notation for e to the 2 pi I times z. Okay, that's just shorthand. Okay, so what is basically this? Well, this is basically, and I'm purposely being vague with this one, approximately. This is 1 if for x in ball of radius 1. Well, why is this true? Well, if x is in the ball of radius 1, sorry, for C. If C is in the ball of radius 1, X basically lives in a ball of radius 1. So X times C is pretty small. It doesn't oscillate so much. And so there's constructive interference from this e to the 2 pi I. So basically, I'm just integrating the ball. Right? So up to dimensional constants, I get 1. Okay? And then if I'm not in the ball, well, if I'm not in the ball, I should get rapid decay. The way to see rapid decay is you just integrate by parts. Right? So like e to the 2 pi I x c, what is that? Well, that's 1 over 2 pi I c d dx of e to the 2 pi I x c. Right? And I can repeatedly get as much decay as I want as long as I'm far away from the origin. Right? If C is not at the origin, then this is an okay integral to do. Does this make sense? All right, so I have rapid decay. And so that's why we're going to pretend that the Fourier transform of the unit ball is the unit ball. Okay? Are there any questions? Okay. And then the third heuristic, third heuristic we're going to use that people use for back of the envelope calculations is the small angle approximation. So heuristic 3. It's also called the phase heuristic or the small angle approximation. I'll call it the phase heuristic. If the angle is small, let's just say it's less than or equal to 1, then E of theta is, I'm just going to say equal to 1. Okay. So I mean, this is clearly nonsense, right? This only happens at 0. But I mean, you could sort of see that this is reasonable to have, right? I mean, so for example, if you just look at the cosine function, okay, cosine looks like that, right? I mean, if I'm within negative 1/100th of the origin, right, then maybe I'm within some value of 1, right? And so up to constants, I'm basically 1, right? So the rigorous version of this is that if I'm close enough to the origin, then my phase, my oscillation doesn't oscillate so much, and so since I'm often just needing upper and lower bounds, I can pretend this oscillation is equal to 1. Okay. Now, you might be wondering, well, like this, they slowly devolve into more and more nonsense. Okay, right? I mean, that's acceptable. This is okay, fine. This is worse than like this is doing like physics. Okay, so there are situations where all three heuristics are actually rigorously true. So, of course, this is not true in R, right? We all know that this is not true in R, but actually, so all three heuristics are actually true. So all three heuristics are true, like literally true, with equals, okay, when one works with harmonic analysis in the p-adics, in QP. So right now what we're doing harmonic analysis over the real field, right? If we work over the p-adic field, actually, surprise, all three heuristics are actually fact. And it turns out actually that sometimes so there have been a lot of applications of decoupling to number theory, and they all go through sort of decoupling over R. In fact, a lot of the application, or maybe I won't say a lot, but at least there are some applications of decoupling for number theory that can actually go through decoupling harmonic analysis over QP first, where the proofs become much shorter because all three heuristics are actually true. Okay? So hopefully I've convinced you that it is possible, like these three heuristics are reasonable to do. Okay? Okay, so given these three heuristics, let's discuss some consequences. Okay? And later we'll discuss even more consequences. So we're going to go on a side note for a while before we come back to the proof of decoupling, because I think it's important to know what back of the envelope, what sort of heuristic moves are good to do, and what are some common heuristics that people use? Okay, so claim one. Claim one. What is the Fourier transform of the interval length R? Well, this is just R times the interval of length minus 1 over R. Okay, and the Fourier transform, okay, this is also just R times the interval 0, 1 over R. Okay. Why? So proof. Okay, this just follows from if we assumed that these were true, and if we knew that these were true, then we change variables, right? Plus change of variables. Okay. So back of the envelope, you can see some pretty quick, I mean, what's the Fourier transform of the interval? Well, it's just the length of the interval times the sort of, you just invert the interval length. Okay. So claim 2. What's the Fourier transform of a box now? Let's say minus R1 to R1 cross minus R2 to R2. What's the Fourier transform of this guy? Well, it's just the area. It's R1 times R2. We don't even ignore, 2R1 times 2R2. No, it's just R1 times R2. Okay. And invert the x coordinate, invert the y coordinate. And you could, these calculations, you can make rigorous, right? I mean, how did we make this identity rigorous? We use the Schwartz function. A Schwartz function over here is basically 1 at the origin and rapid decays outside. And so using that identity, you can upgrade to both these, right? So if you take a Schwartz function adapted to this rectangle, what's the Fourier transform? Well, it's just the main term is R1 times R2 times this guy, and it rapidly decays outside this. Right? Okay, great. So that's a basic calculation, and now let's do a hard calculation, or a harder calculation. Okay. So, so why did I do this? Well, let's now compute the Fourier transform of the indicator function of one of these guys, at least heuristically, at this level. Of course, then if you want to do it rigorously, you would just use the Schwartz function and literally do the same motions. Okay, and then to get the decay outside, you would have to integrate by parts to get it that it rapidly decays outside. Okay, so let's at this level compute the indicator function, the Fourier transform, the indicator function of the thetas. Okay, so claim 3, given I is a to a plus delta, so a is the left endpoint. Of course, if you pick any point inside the interval I, it's fine, because we don't distinguish left endpoint, right endpoint, or the center. Okay, they're all the same. And so theta I, remember, is s squared plus t is the delta squared neighborhood of the interval above I, parabola above I. And we're going to define what we're going to call the sort of a dual tube, t centered at the origin, corresponding to I. This will be the tube, and we'll see later that's very useful. x1, x2, that's the x1 plus 2a x2 less than delta inverse, x2 less than delta 2. So I'm going to draw a picture of these regions all later, and then I will, well, let me slowly move the board up, because v the delta to the minus 1 by delta to the minus 2 tube centered at the origin. And we call it dual to theta I. Okay, then, so let me finish writing and then I'll move the board up here so it'll be readable. Then, what is the Fourier inverse of this guy? Well, it's just E of ax1 plus a squared x2 times the volume of theta I times the indicator function of t, this dual tube. Okay, so let me move this up. Okay, so let me draw a picture of what even these regions are, just to get a feel of what this is even saying. Okay, so let's draw our theta I first. This is, remember, a delta squared neighborhood. This is basically a delta by delta squared rectangle. Okay. Now, this guy is A. There is a normal vector. This normal vector is pointing in 1, negative 2A. Yeah, right, or negative 2A comma 1. Yeah. Negative 2A comma 1. It's the normal vector. Because the tangent vector is 1 comma 2. Yeah. Okay, this is a normal vector. And so what is this tube? What is this tube? This tube is centered. So this is the frequency side. This is frequency on the Fourier side. Okay. Well, I guess there's no frequency inside here right now. Well, I guess there is. And then on the spatial side, the tube, point at the origin, I'm going to take this direction. I'm going to draw a delta to the minus 1 by delta to the minus 2 tube, centered at the origin, pointing in the same direction. Okay. Strictly speaking, I should be drawing a parallelogram here, just like how I should be drawing a parallelogram here. But if I dilate it slightly, then it's no difference. Okay, so this is T0I. Okay, and then this is theta. So that's what this is saying. So if I take the indicator function of this guy, what's the Fourier inverse? It's this oscillatory term times the volume of the rectangle, pretty much, times the indicator function of the dual rectangle. Okay? And you can almost sort of see it already, right? So if A was 0, then this term is in here. If I was sort of the interval at the origin, okay, then that is already true by this identity over here, right? Sort of. So what does this theorem say already? This says that, you know, if A was 0, there's no oscillation. The Fourier transform of the indicator function is the area of the blob times the indicator function of the dual box. Right? And if A was 0, if I have a delta by delta squared box, the dual box, so let's write it. Right? If I had, what's the Fourier transform of this guy? Well, this is just the area, which is delta cubed, times by the indicator function of the dual. Right? That's just this term. And if A is 0, these two statements are exactly the same. Right. Any questions? Okay. Great, so this is just calculus. Let's erase. Okay, so the first heuristic basically says all squares and circles and R and 2R are the same. Hopefully that's acceptable, and this one's acceptable too. So let's erase this board and keep this one.
about the parallelogram.
Mm-hmm.
So the interval has length I at the bottom,
Mm-hmm.
which is like delta.
Mm-hmm.
And then you go delta to delta squared.
Mm-hmm.
And I'm having a little bit of trouble picturing the parallelogram and why the arc length doesn't go into the thing when you look along it. Because the length of it is I down there. But if you look along it sideways, the length is not actually delta, right?
Yeah, I mean, it's like maybe 2 delta, right?
Okay. So what you're saying is that even though the length is not delta, that the arc, because I can't do it that quickly right now in my head, the length that changes by the integration of the arc length is 2 delta?
I mean, I mean, you're basically asking the dimensions of like the parallelogram, right?
So you turn your head sideways, and
Yeah.
it's pointed that way. And then is it easy to see why it's comparable to delta along the path?
Yeah, so okay, so this is delta. I mean, strictly speaking, this is a neighborhood, right? So which parallelogram would you want to approximate it by? Well, you want to approximate it by, so let's draw an even curved piece to exaggerate it, right? So what is this angle? So let's see. So what is this angle? All right, so this, you can compute the slope, right? And the angle here, let's see, let's zoom in. A plus delta, right? And this is delta. And so, and then here's my delta squared neighborhood. And then let's, to draw the parallelogram better, let's use colored chalk. So the yellow piece is the parallelogram, the white piece is literally the parabola. So why is the parallelogram basically delta by, of course this is still the delta by delta squared. Well, it's because, I mean, if you look at the angle, right, like here the angle is basically flat. And then because I'm always above a bounded interval, there's sort of, as my interval goes up and up and up and up, the sort of the angle doesn't increase off to like 90, right? So the angle that this is sort of lies between a bounded range.
The angle that it
right? So if you look at this interval length delta, right? This is basically a completely flat piece. And then if you go all the way up at 1, this is basically up here.
And it grows like the square root of 1 plus the derivative squared, because the parabola, so it's 2x squared.
Yeah, but then since I only live above 0, 1, then that's just a bounded number.
Okay, so
right?
If we only work on this constant in the interval 0, 1,
Uh-huh.
then we're okay.
Yeah.
If you want to look up the parabola.
Yeah, so for you can pick any compact subset of the parabola. So the way decoupling works, you have to pick a sort of region.
Okay.
And then what we're going to do is we're going to pick any fixed interval, a fixed compact piece of the parabola. Of course, any fixed compact piece of the parabola, as I'll talk about later, you can rescale so that it is the 0, 1 interval.
Yes,
Right.
Okay, I agree with this.
Yeah.
I have in my mind that we want to solve something for the wave equation, and then
Uh-huh.
you have the whole wave cone.
Yeah, so even
Wave cone's probably okay, but if it's a parabola and it's curved, then I didn't see the picture.
yeah, so basically in the end, what you do is you pick a subset of the parabola. You don't decouple the whole parabola.
Okay.
Yeah.
And so if you pick a subset, then it's clear that you can just take a rectangle. Okay.
Yeah, I mean, so the size of the parallelogram, of course, will depend on where you are, right?
Yeah.
So
But based on the A, so actually
Uh-huh.
it's proportional to like delta times A to some power or something.
delta times something like yeah.
And that's what makes it work in the equation. Okay.
Yeah, A is just between 0 and 1.
So then you are asking if the interval is away from 0, then I think that you can rescale to the 1, and the particle phase goes through the dp with the constant depending on how many phase.
On where you are, and then you can see.
Yeah.
Okay, yeah, because of
Yeah, there are constants depending on A here, but like since A lives between 0 and 1, or even 1/2 to 1, right? Then it doesn't quite matter.
Our
Yeah.
Thank you.
Yeah. Okay. Okay, great. So let's compute this. Great. So I do this because it's an exercise to use the phase heuristic. Okay. So proof. Also in quotes. Okay. What is this guy? Well, this is just this guy. Okay, and then what is this guy? Well, this is just, let's just write out the region. It is kind of painful, but I think it's worthwhile to go through. Though you may not want to write down each step because it is just, each step is standard, except for one point where I'm going to use the phase heuristic. Okay, so basically the point is that, well, we know this calculation at the origin when a is 0. So if a is not 0, what do? Well, we move a to be at 0, and then we apply this claim over here. The fact that we know how to take a Fourier transform of a rectangle. Basically, we take this, we put it here, and then we apply this result. Okay, so that's the roadmap. Okay, so great. So what do? Or let's shift to the origin and let's change variables. And I kind of want to skip a few steps. So basically, what's the next? You let s prime be s minus a. Okay, and then you collect like terms. Okay, I trust that everyone can do this. So then I'm just going to say what happens when you get the result. You're going to get e of ax1 as a squared x2. S2 plus s squared x2. This term comes up from the fact that what's about to happen is that if I do s prime plus a squared x2, the a squared x2 goes here, the 2as prime x2 term goes here, and the s squared x2 goes here. Okay, and then the linear term I think you can look at. Great. Okay. So so you do your change of variables, you get and reorganize, and you get there. And let's rewrite the integral. So the t integral is actually completely isolated. So let's do. Right? So nothing else. All right, so how do you compute this integral? If you were doing honest calculus, you would break out your other calculus skills. Now let's use the heuristics. Okay. So what's this guy? This is the Fourier inverse of the interval length delta squared, right, of x2. Right? So what heuristically do we know that to be? Well, that's just the length of the interval, delta squared, times by the dual interval evaluated at x2. Okay, basically. Okay? That's just using this identity. Length of the interval times the dual interval. Okay. Now, since we know x2 then is restricted to delta to the minus 2, what's s squared? S squared is s is something between 0 and delta. So s squared is something between 0 and delta squared. And so s squared times x2 is less than 1. And what did our phase heuristic say? If the input is less than 1, then it has no oscillation. Okay. Okay, so this term is basically 1 by the phase heuristic. This term is by claim 1. Okay. And then what else do we have left? Well, we have one last term here. We just have this guy over here. What is this guy? This is the Fourier inverse of the interval length delta evaluated at x1 plus 2ax2. Right? Because this guy is now gone by the phase heuristic. So what is that? Well then, this guy is then just, so it's the Fourier inverse of this interval, which is just, so what's the answer? Well, it's the length of the interval times by, I'm running out of space. Nope, should not write. Let's just use another board. What is this guy? Well, this is just basically the length of the interval times by the indicator function, the inverse of the interval, evaluated at this point. So that's just x1 plus 2ax2 less than delta inverse. So what did we just get? We got that the Fourier inverse of that guy is delta cubed times by x1 plus 2ax2 must be less than delta inverse. That's this guy. And x2 must be less than delta to the minus 2. That's this guy. That's the indicator function of t01. And of course, since we're in a, as was mentioned, we have a delta cubed here. So what's the volume of one of the theta i's? Indeed, as we just discussed, since it's a finite compact interval, each of these little parallelograms or these neighborhoods have volume delta cubed. Of course, depending on where I am, but yeah, depending on like sine of A or something, or yeah, and then so that's how I get the volume of theta I here. Yeah. Are there any questions? And of course, you can make this rigorous just by using the Schwartz function. You would use the Schwartz function to see that you do get this term inside t of 0, 1, and then outside of t01 on its dilates, you get rapid decay, as much decay as you want. And to do that, you'd have to use the integration by parts. Okay, so since I've already talked for an hour, maybe we take a break for 5 minutes. Okay. Yeah, 5-10 minutes. So we just took a little sidetrack, and then we made this computation. And the reason why I did this computation, remember, was to show that the decoupling constant, dp of delta, is bounded below by this expression over here. And just to remind you of what everything is again, or just have a board where everything is defined. So let's see, so I is in T delta, theta I is defined to be delta squared, and then dp is okay. And then Bourgain-Demeter result is that dp of delta okay, so just to rehash quickly all the notation. Okay, so we did this calculation, this Fourier inverse calculation over here, at least heuristically. One was to show you some of the heuristics that are used. Two was also that we were going to show this lower bound. And I'm going to, of course, show this lower bound using this estimate, which, of course, relies on heuristics. Now, of course, to make this rigorous, you have to make this rigorous. And how do you make this rigorous? Use Schwartz functions. Okay, this is when I wrote this, and to make this rigorous, the only difference is that everywhere you see an indicator function should be a Schwartz function adapted to a certain region. Okay. Okay, so why do I get the lower bound? Okay, so how do you get lower bounds for decoupling constants? Well, you need to write down an f for which its Fourier transform supported in a delta squared neighborhood, and you compute the left-hand side and the right-hand side, and you compute the ratio of this guy to this guy. Okay, so let's write down two f's. Okay, so this one is easy. So proof. Okay, so y is dp of delta bigger than 1. Okay, well, so which f do I pick? Well, I'm going to take f to be the indicator function of the piece of parabola that lives above 0 delta, the inverse. Okay. This guy lives, so where does this guy? So let's remember the definition of theta I. This is just s squared plus t, s is an I, t is less than delta squared. A delta squared neighborhood of the piece of parabola that lives above I. So this is a delta squared neighborhood with a piece of parabola that lives above 0 delta. Okay, well, of course, this is also a valid f to pick, right? Because decoupling says, for all f whose Fourier transform is supported in a delta squared neighborhood of the piece of parabola above 0, 1. Of course, this is a subset, right? So then the LP norm of this guy, I don't even need to compute anything. We're just going to write this as such. And then what's the right-hand side? What's the decoupling right-hand side? Let's call it well, as I run through I from 0 to delta, well, the only one that's valid is when I is equal to this interval. Right? Otherwise, the function is 0. So this is also just the same thing. All right, and of course, then you take this guy, divide by this guy, and you get 1. Right? The decoupling constant is at least 1. So that's the easy example. Okay? Now, I guess since it's easy, I'll just put it down here. Okay, well, we'll lift it up a little bit. Okay, so now let's see, where do we get this term? Okay, this is the interesting term. Okay, let's erase this board. Let's see why we get a lower bound of this guy. And you might ask, well, why did we even care about this? Well, because if p was like 2, then this is a positive power delta. Okay, so okay. Y is dp of delta bigger than delta to the minus 1/2 minus 3 over p. Okay, so now we're going to do something interesting. So we're going to take f to be, of course, by definition, it's just this guy. And f theta I is going to be defined to be, on the Fourier side to be delta to the minus 3 indicator function of theta. So I can take f to be this, right? So in other words, I'm going to take this guy. Okay, I'll pull it out of there, and let's compute both sides of the decoupling constant. All right. So what does this say? What does this say? What does this say about f theta I? Well, now let's use this calculation that we just did. Right? We know what the Fourier inverse of 1 theta I is. Right? So we get a delta to the minus 3. This cancels off with the volume of the theta I. Or if you don't want to do that, you just put inverse of the volume. Okay? So you get that this is an oscillation, ax1 plus a squared x2 times the indicator function of t0I. So remember the picture. So when one starts, at least when I started, I always wanted to try to keep in mind and try to do this without drawing pictures. then you learn that everyone draws the pictures and no one really writes down the formulas. So the most important thing is to remember the pictures. So what's T01? So this is I. I have a vector here. I take this direction. I draw a tube centered at the origin of dual size, delta to the minus 1, delta to the minus 2. And this is T0I. Okay? So now we have a good picture of what this identity says. Okay? So f theta I is this guy, is the indicator function of this guy with some oscillation, which I've conveniently actually drawn a wave. So it's some oscillation times the indicator function of this tube, and of course rigorously then the wave sort of decays rapidly outside. Great. So let's do something easy first. What's the LP norm of this guy? Right. So remember, so how do you compute LP norms? So the back of the envelope way to compute an LP norm is just, L1 norms are just base times height, right? So a function, has a typical base and a typical height. So what's the L1 norm of this? So base times height. So the L1 norm is base times height. What's the LP norm? It's just height times base to the 1 over p. Right? So let's do the back of the envelope calculation. So what's the LP norm? Well, this function has height 1. Right? This function has height 1. And what's the base? Well, the base is one of these tubes. And what's the volume of the tube? It's delta to the minus 3. And so what's an LP norm? It's delta to the minus 3 to the 1 over p. Right? Okay. So let me write it a little bit better. Okay, so what's the decoupling right-hand side? Well, of course, this is a squiggly, because this is heuristics. So that means this is a squiggly, and this would be a squiggly. But let's not be so precise at this time. So what is this? Well, I got 1 over delta many terms. Each of them costs delta to the minus 3 over p squared to the 1/2. So I get delta to the minus 3 over p squared to the 1/2, and then this delta inverse gets raised to the 1/2. And so far? Right? So each of these guys is worth delta to the minus 3 over p squared to the 1/2 gives this guy. The number of terms is delta to the minus 1, gets raised to the 1/2, so I get this guy. Okay. And of course, to make this rigorous, you'd use Schwartz functions, but let's not do that. Okay, great. So now what about the left-hand side? What about this guy? So we know what this is equal to. If we can compute this, we just take the ratio. And we don't actually even need to know exactly how big f is. We actually just need a lower bound on how big f is. Right? So let's look at f. Okay, so what is f? Let's do some pointwise calculations first. So f is sum I and p delta f theta I. And we know that this guy is sum I and p delta e of ax plus ax1 plus a squared x2. And a depends on I. So as I was writing the notes, I noticed I omitted this. A depends on I. It's the left endpoint of I times the indicator function of these tubes. Okay, so what does this look like? Well, let's draw the picture, right? We drew one of these waves. Okay, what do the others look like? Well, so let's draw the picture. So as I ranges from here, the directions of these tubes, this one might be vertical, and these tubes, they slowly become more and more, I'm exaggerating, so I want to draw the effect. They sort of, and so maybe the tube corresponding to this guy is vertical. And as I get more and more, they get sort of tiltier and tiltier. I don't know how to say this, but so I get this little bush. Okay, and each one of these tubes has a little oscillation attached to it, and I'm just going to draw one of them. Otherwise, it's too messy. Okay. Now, at the origin, So here's the origin. At the origin, there's no oscillation. There's this big spike at the origin. There's constructive interference at the origin, right? So then I know how big. At the origin, I know that this guy is there's this big spike. So if you look at this picture on its side, it would be some oscillatory mess, and then this big peak down here, right? If you take this picture and sort of put it on your hand and then looked at it on its side, right? There's a giant peak at the origin. Okay? In particular, this peak sort of lasts inside a ball of radius 1. Right? So for x inside a ball of radius 1, and when I write 1, you could really think of it as 1 millionth. There exists an absolute constant, let's say 1 millionth. So for x inside a ball of radius 1, we have constructive interference. And so, when x is in a ball of radius 1, each of these guys, sort of it doesn't oscillate so much, let's pretend it doesn't oscillate at all. And then at the origin, this is equal to 1. So I get the number of terms in here. So then f is approximately delta inverse, which is the number of terms I have here. Strictly, to do this rigorously, you basically just observe that cosine near the origin is at least like 1/2 if x is within like 0.01 of the 0. Right? Okay? So now why does this help? Well, this gives a nice lower bound. So what's the LP norm of f? Well, I don't know. Let's just bound it below by the LP norm over a ball of radius 1, or 1 millionth. And I know that my function has height delta to the minus 1 there, and the base is a unit ball. So this is delta inverse. Okay. Great. So now we have a lower bound and we have an upper bound.
So the 1's 1 over here, right? Or no?
No, because it's the height. It's base to the 1 over p, but the base is of size 1. Yeah. Okay. So now, what do we have now? Well, what do we have? Where should I write this? Maybe. Okay. So so what do we have? We have that FLP is at least delta inverse. And we know that the right-hand side is at most, is equal to this guy. Right? So, let me just erase stuff on the board. What should I erase? Okay, sorry, I'm going to swap the boards a little bit more. Let's erase this part. Okay. So, dp of delta is at least f and LP for some I and p delta theta I LP squared to the 1/2. We know that the numerator is at least delta inverse. The denominator is this guy, delta to the minus 3 over p, delta to the minus 1/2. So this is delta to the minus 1/2 plus 3 over p, which conveniently is exactly the bound that we want. Right. So, yeah. So Bourgain-Demeter's bound is actually more or less says that this lower bound is more or less sharp. Okay. So this is just one example that shows that Bourgain and Demeter's theorem is sharp. There is another example that shows this lower bound, and it's the number theory example. It's the exponential sum example. That f is Fourier transform supported in a delta squared neighborhood of the origin, and I've partitioned it into sort of regions, delta by delta squared regions. So the number theory example corresponds to taking the function f hat, where f hat is a Dirac spike, right? Because the Fourier transform of a Dirac delta function is an exponential, e to the 2 pi of something, and so that quickly corresponds to an exponential sum. And then there you can perform a similar analysis of looking at where the places of constructive interference are, and then you can see that you will actually quickly get another lower bound like this. But I like this example better because, so the number theory example is more from the number theorist, and this is the harmonic analysis example. They're sort of almost, it's also like dual to each other. But we'll talk more about the number theory in a later lecture, hopefully. Okay, so that's the lower bound.
So lower bound actually works for any p, but upper bound is p bigger than 2.
Lower bound is, yeah, let's see. So, yeah, now if p is equal to, so this lower bound, right, if p is less, between 1 and 2, I still only get, this is a bad bound if p is equal to 1, right? Like, the lower bound that says that d of, let's say, 1.5 of delta is at least 1. Well, that's sort of trivial. Yeah. Yeah, in the decoupling bounds, yeah, we do need the fact that p is at least 2. Yeah.
That's a question from earlier, is that the people want something like that to be less than 2. Is it interesting?
I don't think so. Yeah, mostly. Yeah, I think all the bounds that people care about are all at least at the, you know, at least p at least 2.
So you have some object that you want to make estimates for on something.
Yeah.
And if p is bigger than 2, then you can apply the decoupling,
Mm-hmm.
apply it to the pieces which are.
Yeah. Yeah, I think all the interesting terms are all the interesting, at least all the interesting applications of decoupling so far, all valid for terms p bigger than, for L2 LP decoupling for p bigger than or equal to 2. Yeah. Yeah. There are you'll see later in the proof, there are reasons why we do, it's extremely useful to have p bigger than 2. Sort of, one sort of reason why is that, so I'll talk about this later. There are estimates. So one thing you could do is you could sort of spatially localize to, now let's say another region, okay, let's say another region B. For some technical reason, you want to spatially localize your problem even more because maybe there's good decoupling properties there. And so if you partition R2 into balls B, and you sort of have, this is what's called local decoupling, having p bigger than or equal to 2 allows you to sort of patch these local decoupling estimates into a global decoupling estimate. Here I've only talked about global decoupling, so that it's technically simpler. But later we'll see that p bigger than or equal to 2 is a useful thing to have. Not just for this reason. There are also other reasons to have p bigger than 2. Yeah. Okay. So let's see. What is the next thing? Okay. So great. So let's go back to So we showed that Bourgain and Demeter's decoupling, parabola decoupling result is essentially sharp, because we gave the lower bound as this guy, and Bourgain and Demeter just proved that the upper bound is basically delta to the minus epsilon times the lower bound. Right?
So I'm guessing for high dimension Parabola, choose 3 to dimension 1.
Not quite right. So the numerology is d plus 1 over d, or d minus 1 over d plus 1. Yeah. Okay. So the critical x. So the yeah d plus 1 over d minus 1. Right. When d is 2, this is 3. Yeah. Yeah. So there is a sort of critical exponent, right? And the critical exponent happens when these two terms are equal, right? If you have two terms in analysis, you set them equal, and that's sort of the critical exponent. So these two terms are equal when exactly p is equal to 6, right? So let me write that down. Okay, so BD 14, dp of delta 4, p at least 2, dp of delta is at least Okay? And so what do we already know? d2 of delta is equal to 1. D infinity, which is covered by this theorem, right? It's saying that this term is dominant. And if d infinity of delta is at least delta to the minus 1/2, which is this term, right? So there's a transition point. And the transition point happens when d equals 6. d of 6 of delta is when these two terms are the same. And I would want to prove this estimate. Right? Okay. So p equals 6. So p equals 6 is the critical estimate. Okay. Now, there needs to be a little argument done as to why. So it turns out that if I'm able to prove this estimate, then I can prove the decoupling estimate for all p between 2 and infinity. The one sentence proof is that it follows by interpolation. Right? If you go and compute the if I know the p equals 6 estimate, then I interpolate with the p equals 2, and then you quickly realize, this is delta the epsilon. If interpolation works as you wish it would, then you would get that dp of delta is less than delta to the minus epsilon between p between 2 and 6. Similarly, if you interpolate these two estimates together, then for p bigger than 6, then you get this term. The problem is that how do you write this problem in terms of an interpolation estimate? What's the operator? Right? There's no operator. Right? The function appears on both sides. Right? Okay, so let's briefly. This is a somewhat technical thing, but let me briefly summarize what I just said and then illustrate how one might want to turn this into it. What's the operator if you want to interpolate it? Okay? Okay, so it turns out that you can interpolate decoupling estimates. Okay, so the theorem is the theorem is easier to state than the proof. So if 1 over p is theta over p naught plus 1 minus theta over p1, then dp of delta is controlled by some constant depending on p naught and p1 times by dp naught of delta to the theta times dp1 of delta to the 1 minus theta. And upon writing this, I realized I've used theta for different things, but hopefully it's obvious from context. Okay, so this would be an estimate that, if I told you, this was an operator norm bounded by operator norm to the theta, and this looks like a typical interpolation estimate, right? And of course, so I guess exercise, assume theorem, and that d6 of delta is bounded by delta minus epsilon. Prove then that prove dp of delta is bounded by for all p bigger than 2. Right? Yes?
So is this integration flexible for any other situation?
Yes. As in for arbitrary decoupling, like decoupling anything. Yeah, so these theorem so this theorem is the proof of the theorem is quite flexible. Now, oftentimes what you do is you prove the theorem, or you just assert that it's true, depending on how much you want to write. The proof of the theorem is pretty flexible. It depends on the region, depends on, is it L2 LP, or do you want LQ LP, LP LP? the proof is sort of, the idea of the proof is more important than what the theorem actually says. But usually, if you want to prove a decoupling theorem, there is an interpolation theorem available. You just have to actually prove it. Yeah. There's no, as of right now, there's not very many results that say, take an arbitrary manifold omega, partition it in so that's locally flat, then we have a interpolation theorem. Although I think everyone believes that this is true. Usually it's just done by, okay, well, here's a case-by-case thing. So that's an exercise. So now let me illustrate how to do it. Okay, so how to prove interpolation. Sketch. Okay. There are a few points which I'm just going to hand wave past. So I should say that it's not necessary to prove the interpolation theorem to prove this estimate. You could just prove this theorem directly. The Bourgain-Demeter, my proof, and Guthmall, they're all robust enough to just fix an arbitrary p bigger than 2. Your proof will slightly differ between p bigger than 6 and p less than 6. But you could prove it directly. So this is technically extraneous from the discussion here. But it is a useful tool to have that, like, if you know that these two, you just have to prove one estimate, the L2-L6 decoupling. Okay? Okay, so how do you prove this? So let me write down the operator first. So we're going to write, so P delta is the partition of 0, 1 interval of length delta. This will be, I'll just number the intervals I1 to IN. Okay? And we're going to define the operator. Okay, so what does it do? It takes a collection of functions, arbitrary functions. I don't put any Fourier restriction to them. It takes n functions, and it sends it to Fourier restriction to theta ij fj. And this is just defined to be fj, or let's do it this way. What does this mean? This means p theta ij f is defined on the Fourier side to be f hat times the indicator function theta ij. Okay, so Fourier projection to theta ij. Okay. And these are arbitrary functions. So that's my operator. Now, we're going to make one more assumption on the theta ij's, and we're going to talk about it later. And this is why it's called the sketch. So suppose that this operator, Fourier projection to these curved pieces, is bounded in LR, is a bounded operator for all shorts F, and let's say at the two places that you're supposed to interpolate, and R equals P naught and P1. This is not quite true, because remember Pfefferman's Fourier projection to a ball, the ball multiplier is not bounded. But we can fix it because these neighborhoods of the parabola are basically parallelograms. And Fourier projection to a parallelogram, because it has 4 sides, is bounded in LR or any LP space you want. Okay, so you do need to tweak this proof in a kind of annoying way to account for the fact that this is not actually true, but it's a doable thing. But let's assume that this is true. Okay, how would we proceed? Okay, so then then for r equals p's naught and p1, what's the LR norm of this operator acting on this a collection of functions? Okay. Well, well, by definition, this is just the LR norm of this guy. And I know how to decouple it into intervals of size delta. Okay. And let's be pretty pedantic. This is my function for heuristic to one of the individual pieces, right? And to do so, to bring the LR norm in, it had cost me d of r. Right? Good so far? Okay. Now, this function, for heuristic to theta ik, is literally just the kth term of this sum. So what is this? This is just dr delta sum k from 1 to n for a projection of theta ik of fk Lr squared to the 1/2. Now, let's use the assumption that for a projection to this curved piece, which is illegal, but let's do it, is a bounded operator. So, when I do so, this is bounded by some constants. Okay, let's ignore it. Let's put an r here. Okay, dr delta k equals 1 to n fk r 1/2. And that's great because this is just dr of delta times by the L2 norm of these functions when I first do it in LR. So I guess I'll write the norm as L2 of LR of RD. Right? So T is an operator that takes the function in this space, that collects the sequence of functions in this space, and maps it into LR for R equals P naught and P1, and the operator norm is the decoupling constant of size R. Okay? And so I know it at P naught, I know it at P1. What do you want to do? You want to apply Reed's theorem, which is true for these types of operators. And so in the interest of time, you apply Reed's theorem, and then you get this estimate over here. Okay. So how do you patch this? How do you patch this annoying effect up? You know that these are curves, so this is not quite true. Well, what you actually do is there's actually a family of decoupling constants that are actually equivalent to each other. So here I'm going to be a bit more vague. Here, let's erase this. So let me draw two technically different decoupling constants. Here's decoupling constant 1, where these are interval size delta. And then here's decoupling constant size 2. So this is the standard one that we've always been working with. Here's the second decoupling constant. Okay, maybe I draw it so that's the same. And what I'm going to do is these are made out of parallelograms. So this is decoupling constant 2. So to fix this and to use, so you know that this estimate is false when I'm in these curved pieces, and it's true when I have these yellow pieces. Okay. So to fix this proof, the last thing you need to prove So if you want to do it rigorously, you have to use these yellow pieces, and then you run through it, and then you run through the argument. You realize that there's one more thing you need to prove, is that you need to prove the decoupling constant for the curved pieces is equivalent to the decoupling constant for these pieces. Now, this is, at least heuristically, it's not so bad to see because delta is already very small, and each of these curved pieces is contained inside a rectangle and contained outside a parallelogram. Furthermore, just to justify that these are actually the same, if you want to do harmonic analysis over QP, actually these are the same. The QP world does not see the curvature. Okay. So I'll just leave it at that. Hopefully it's slightly not pleasing, but the last thing you need to do to patch this together is to show that these two decoupling constants are actually the same. But that's just a technical detail that I think is best left to the references that I mentioned. Okay. Is there anything else I would want to mention? I guess let's see, I still have 6 minutes. Okay. So what did we just do? Well, we basically said that in order to prove the Bourgain-Demeter decoupling estimate, we just need to prove the L2, L6 estimate. Okay. Right. Okay, so let's end with one last comment about decoupling. Okay, so right, so what do we want to show? So theta I, right, so now it remains to show that the L6 norm of F is controlled by delta to the minus epsilon, some I is an interval length delta that partitions 0, 1, F theta I, L6 squared 1/2 for all F with Fourier transform supported in a delta squared neighborhood of the piece of parabola that lives above 0, 1. Okay, and theta I, remember, means delta squared neighborhood. Of the piece of parabola that lives above I. That's the estimate we just need to prove, and I mentioned roughly here why you just need to reduce to the p equals 6 estimate. Okay, now there's a similar estimate that had already been proven before. So the following estimate is known, or was known before parabola decoupling. Well, it was known much earlier than decoupling. So we have a result from the 70s of Cordova and Pepperman, or Cordova worked using their estimates. And it's that the L4 norm, so it's called the reverse square function estimate, okay. The L4 norm is controlled by the L4 norm of these individual little pieces. So here, the difference is that the L4 norm is on the outside. So I do my pointwise L2 norm first, and then do an L4 norm. The difference in decoupling is that I first do my LP norm, and then do the L2 norm. Okay, so this is known. The proof of this, so we're not going to go through the proof of this, the proof of this really involves the fact that 4 is even, right? 4 is 2 times 2. Now, why is decoupling easier? So first of all, this is actually the higher dimensional version. So you can imagine that these theta I pieces are a thin sort of slab, a thin piece of the parabola. You can imagine that you could formulate a similar conjecture for the paraboloid. That conjecture is as difficult, is probably more difficult than the restriction conjecture, or the Kakea conjecture, right? So why is this hard, and why is that easier? Well, there's a difference, right? So first of all, you can see this estimate implies an estimate of this form. Because since 4 is bigger than 2, I can use Minkowski, or that's not true, since I just use Minkowski, 4 is bigger than 1. I use Minkowski and bring the L4th norm inside. And I already get an L2, L4 decoupling estimate. If you put 6 here, this estimate is false. You can play with some examples and see that this estimate is false. So why is this estimate better than this estimate? Why are decoupling estimates sort of easier to prove than these reverse square function estimates? Well, it's because there's this little observation here that you see, what does the decoupling estimate say? Well, it says the L6 norm is controlled by the L6 norm of a smaller piece. So what I can do is maybe I can't prove decoupling all the way down to scale delta. Let's say, as a first step, I can prove decoupling all the way down to some intermediate scale. Then I've reduced the problem from decoupling f to decoupling f at an intermediate scale. And then I rescale, and let's do it again, and again, and again. This decoupling estimate is very sort of nice in terms of it allows for iterations. Because, just because of how this thing is built. On the other hand, this reverse square function estimate, there's no way to have, if I control f by sort of the square function at a smaller scale, how do I iterate this? It's a pointwise thing. Right? So this is what makes the reverse square function estimate, even though it looks similar, it's just a little, I just literally reversed the norms. This estimate, or these types of estimates, are much harder to prove than decoupling estimates, in general. Of course, in this case, you can prove it directly. Next time we're going to start with actually the proof of this, and one of the first things we're going to prove is the parabolic rescaling lemma, which basically says that if I know how to decouple a little piece, then, so if I know how to decouple the whole thing, how much does it cost to decouple sort of one little piece? Right? So then, that's one key iterative step. Yeah, okay. Are there any questions?
So you wrote down the reverse square function estimate. Do you mind, I forget when you're on which side of 2, what the square function estimate is. And can you comment on how that relates? Because this is decoupling, right? You take the function and you write it in Fourier space in terms of these pieces. There is there's the reverse estimate, right? There are estimates. Reverse estimate.
Yeah, there are estimates that go this way.
And one of these, but then neither one of these looks like
Neither one of these looks like decoupling estimates.
Because the decoupling estimate, this is like a norm in like a Besov space.
I guess. I don't work with Besov spaces, so yeah.
Okay.
Yeah.
Okay, so neither the
Yeah, none of them apply. Well, I mean, so this estimate implies, just by Minkowski, it does imply this estimate. This estimate, I just bring it in. It does imply this estimate.
Wait, you bring it in.
How
many terms are in that sum? That's even if that sequence is infinite?
Oh, I just use Minkowski and interchange the L4 and L2 norm. Yeah. So because 4 is bigger than 2, because 4 is bigger than 2, you can interchange the L4 and the L2 sum using Minkowski, and then you get this guy.
Delta?
No, this is an absolute constant.
But I thought for P96,
So actually, yeah, so the lower bound, right, this is a positive power of delta. Right. So actually, this does show that the decoupling so not only do we know that D2 is equal to 1, so in the case of the parabola, D4 is actually equal to 1. It's actually by interpolation, you know that for p between 2 and 4, it's delta to the minus epsilon, or a power of log, if you want to be even more precise. Actually, it's more or less conjectured that for p strictly less than 6, it should be, dp should be of size 1. And Bourgain did give an example which said that at p equals 6, dp needs to lose some power of log. But yeah, so the only relation between reverse square function estimates and sort of decoupling is that, yeah, using Minkowski, you can, if you have this estimate, you can actually recover L2, L4 decoupling for the parabola, but that's subcritical, right? That if you knew this estimate only, you wouldn't be able to prove the full Bourgain-Damodaire decoupling theorem. Because if you only knew, right, so if you only knew that, let's say, d2 of delta is equal to 1, d4 of delta is basically 1, and you knew that d infinity of delta is controlled by delta to the minus 1/2, what would this say about d6, right? You would only be able to get the estimate from interpolation, right? And so that's worse than what the theorem says. Yeah. So, yeah. In higher dimensions, this 4 is replaced by, so if you want to talk about the d-dimensional, and I guess when I say d-dimensions, I mean time is one of those dimensions. The 4 is replaced by 2d over d minus 1, and the 6 here is replaced by 2 times d plus 1 over d minus 1. So when d is 2, this is 6, and d is 2, this is 4. Yeah. So this is the Strickhart's exponent. This is the square function exponent, just to point out some higher dimension numerology. Yeah, and in general dimensions 2d over d minus 1, this is harder than the restriction. There's yeah. Yes?
So can we recover square function estimate from decoupling for
Probably not. Yeah, so there is this paper, now okay, so let me just, there's this paper by Larry Guth, Hong Wang, and Rixiang Zhang, who prove a square function estimate for the cone in 2 plus 1 dimensions, so the first non-trivial case. And they don't use decoupling, nor do they use polynomial partitioning. But they're somehow able to sort of rewrite their reverse square function estimate in a way that it becomes more iterative. And I guess they use sort of, ideas similar to the proof of decoupling, right? In that, they look at wave packets and how the geometry of the wave packets interact and stuff like that. There isn't any theorem so far that says, like, okay, I just need to prove a decoupling estimate, then I get a reverse square function estimate. There's been nothing like that so far. Yeah. Any other questions? Okay, well, that's all I have for today then.
Okay, thank you very much.